Today we're going to be looking at Undecided with Matt Ferrell. Specifically, this will power everything. A Mr. Clean magic eraser. Just kidding. The video is called Why Thorium Will Change the World. Those of you who don't know me, I'm Tyler Folse. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry. From engineering to operations to emergency response. I don't claim to know everything there is nuclear, but I can certainly share some knowledge. Let's see.
Thorium reactors are like the solid-state batteries of nuclear power. Vastly superior, yet forever on the horizon. But now a Danish company is closer than ever to turning them into a reality. Its reactors are designed to deliver on thorium's decades-old promise, a self-sustaining chain reaction that breeds fresh fuel, making energy cheaper and more abundant than ever.
So I can understand some of the hype behind it. It is more abundant than uranium, naturally, and it can produce less transuranic, high-level waste. And it is somewhat resistant to proliferation.
These aren't just thorium reactors. They're small modular reactors designed to function as shipping container-sized, self-maintaining batteries that operate reliably for years. So how is this company tackling such an ambitious engineering challenge? When might commercial thorium reactors finally arrive? And is thorium the missing piece of the clean energy puzzle? I'm Matt Ferrell. Welcome to Undecided. This video is brought to you by Surfshark.
I wouldn't necessarily anything as sort of a missing piece to clean energy necessarily. I could see it working hand in hand with uranium, but even building more uranium reactors at scale would also help solve that. I'd like to see both.
In the 1950s and 60s, the Atomic Energy Commission sought to transform nuclear energy from a source of fear into a source of energy too cheap. Why don't we have
That isn't very much. I mean, it was really an experiment. To give you a sense of scale, a full-size nuclear power plant produces well over 3,000 megawatts of heat, which figures out to well over 1,000 megawatts of electricity.
this limitless thorium energy today?
Well, first off, it's not limitless. It has limits just like uranium does.
Because the project was defunded after the Atomic Energy Commission shifted its research focus to a different kind of breeder reactor, which too was plagued by technical challenges until its own cancellation.
One other disadvantage, or it was really a disadvantage as seen back then, which is ironically seen as an advantage in today's world, is uranium is more flexible for weapon and naval use. A lot of the early nuclear reactor designs were, let's produce power and let's also stock up on weapons for the Cold War. That's just one reason.
As for Weinberg, he was fired for continuing to champion thorium. He wrote wistfully in his memoir, "I hope that in a second nuclear era, the molten salt technology will be resurrected." Weinberg's wish might just come true thanks.
So molten salt and thorium aren't necessarily synonymous. I mean, thorium does have compatibility with molten salt reactors, but you could also use mixed oxide fuels. You can use a combination of uranium and thorium in the same reactor, for instance, if one of them is scarce for some reason.
To a Danish company. No, not that kind with icing and almonds.
I was wondering if that was going to come up. Hey, I bet you could. That would be awesome, though. If you could use a Danish company that powers all of their production facilities with thorium reactors.
That's a pretty sweet solution for a different kind of energy slump. Copenhagen Atomics is a startup out of Denmark, reviving Weinberg's hopes for a so-called breeder reactor, one that creates more fissile fuel than it burns. And they're one of the handful of companies answering the call for cheaper nuclear power with small modular reactors.
Yep, that's a real thing. Breeder reactors, again, don't necessarily have to have thorium in the mix. After all, thorium isn't a direct fissile material by itself, because you're actually comparing fissioning uranium-235 versus uranium-233, because thorium-232 absorbs a neutron, becomes thorium-233, couple of beta decays later, and then you get uranium-233. So people are throwing around the word thorium, but you're really comparing uranium-233 versus uranium-235. And 233 actually does release a little bit more energy than 235.
And when I say small, I mean Copenhagen Atomics reactor is designed to fit inside of a standard 40-foot shipping-sized container.
That's cool. Something like that would be great for disaster relief during a crazy loss of power hurricane or something, or or just getting power to remote areas. You can also have them just not produce electricity. You can just have them produce heat. You just need a heater.
And by modular, I mean they aim to mass produce 1 reactor per day on an assembly line, then truck as many as needed to a plant site to hit the desired power output.
And that's, yeah, I guess you could mass stack them. What do we have, a 30-pack of reactors? Probably get that at Costco. But yeah, it's a lot more scalable. You can put them all together, or you can have one isolated truck in a small remote area.
Nuclear reactors like this could make them cheaper to build and easier to scale with rising energy demand. And because they're building the same design over and over, they can work out the kinks in the manufacturing process, which means delivering reactors at a predictable cost.
That is one challenge associated with building the large-scale ones, is you got to get the permitting, the zoning, all of the pre-approvals, and for one big, massive site. And then what you got to do is you have to essentially build it custom, because something that big just isn't modular. Now, yes, you still have, they're still going to have regulatory hurdles to get over. And even where they decide to park these trucks, there's reactor site criteria associated with that. But it's easier.
Instead of the massive overruns that have plagued large, custom-built nuclear power plants. I'm going to let CEO and co-founder...
Which every large nuclear power plant is going to be custom built.
Thomas Jan Peterson explain how they're fitting nuclear reactors into a box. But first, a refresher on nuclear chain reactions. You probably know uranium as the go-to fuel in conventional reactors.
This is an interesting little model. He actually modeled all the electron shells in there. That's interesting.
When struck by a neutron, uranium-235 split.
Okay, and there he took it out. Because I was going to say the electron shells are completely irrelevant in nuclear reactions. It's all around the nucleus, and the nucleus is, if the atom was the size of a baseball field, the nucleus would be a mosquito on second base. A very dense mosquito that has over 99% of the mass of said atom.
Releasing a huge amount of energy and a few neutrons that go on to split more uranium-235. If there's
not a bad animation, he's showing 2 to 3 neutrons showing up, and I like that he didn't label the fission products, because it really is, there's no 2 set fission products. It's a probability spectrum of what you're going to get.
Enough fuel and moderator like water to slow these neutrons down. The chain reaction sustains itself, producing heat to make steam, then that store uranium-235. If there's enough fuel and moderator like water to slow these neutrons down, the chain reaction sustains itself.
Okay, he got the part about moderation right. There's a lot of misconceptions about there that the water actually slows it down so it lowers power. No, moderation is going to raise power because it's going to increase the probability of it causing a fission.
Producing heat to make steam, then that steam spins a turbine to generate electricity. The Nuclear Energy Agency estimated that worldwide uranium reserves will only power us for another 200 years at current consumption rates.
Okay, cool, it went up. A lot of data showed it was something like 90, and that is just the fallacy of using proved reserves. The numbers are always going to be off. Like, peak oil is always 20 years away. Peak uranium looks like it's even further away. So, hey, that's cool.
More recent estimates emphasize the importance of new exploration and processing techniques that will be necessary to expand its usage into the future.
Could even get it from seawater, not completely unheard of. And you could also become more fuel efficient with it, have uranium and breeder reactors. That can extend 200 years to something ridiculous like 20,000 years, but people are already looking at 200 years like it's still a pretty long time. Maybe we'll have fusion in 200 years. That one always seems 20 years away.
Shared in a recent episode of the revival of old nuclear power plants to power data centers, nuclear energy is set to expand worldwide as we reach for low-emission solutions to today's booming energy demands. However, there's a solution to uranium scarcity, and that's another element.
The other solutions to scarcity are breeding and reprocessing. But using a substitute like thorium or even combining it in mixed oxide could also work.
Thorium. It's not only 3 to 4 times more common in Earth's crust, because only 0.7% of natural uranium is the chain reaction forming 235 variety. Thorium is actually nearly 500 times more abundant than the uranium that we rely on for nuclear energy today.
It is, though thorium doesn't cause fission.
Now, thorium can't form chain reactions like uranium-235,
like you said, good.
But if thorium is seeded with a little uranium-235 or plutonium-239, which are both fissile materials that release neutrons when they split, then thorium-232 can absorb a neutron and become thorium-233, which beta decays into protactinium-233
the intermediate
and then
step.
into uranium-233. And this is the clever bit.
Not a bad explanation. One other thing about plutonium-239 is we do use it in uranium-235 fueled reactors, and that's because uranium-235 is in there with the uranium-238. The enrichment is on the order of 2 to 4%, depending on which fuel assembly you're talking about inside the reactor, but the remaining 96-98% is uranium-238. That's going to absorb neutron, become uranium-239, which another couple of beta decays is going to become plutonium-239, which is significantly more reactive than uranium-235. So what this looks like is at the end of core life, the reactor is going to respond faster because it has a significant percentage of fissions can be on the order of 20% can come from plutonium-239. Now, it doesn't produce enough plutonium-239 that it is a breeder. You're still going to deplete your fuel, but you get a little bit of extra fuel efficiency out of it.
Because uranium-233 is fissile, it splits and releases neutrons that sustain a chain reaction.
One good rule of thumb, it's not 100% accurate, but things with odd numbers have a tendency to be fissile. There's another word called fissionable, like uranium-238 is technically fissionable, but it has to be a fast neutron, and that's a pretty low probability because reactors don't have nearly as many fast neutrons, not enough to sustain, and the odds of a uranium-238 undergoing fast fission are significantly less than a uranium-235 undergoing thermal or slow fission.
Whereas chain reacting uranium-235 in an old school reactor just eats up more fuel, the neutrons split out from the uranium-233 create more fuel from thorium. But how?
And those 2.35 neutrons gives you a little bit more because you need one of those neutrons to split the next uranium atom in the chain reaction. And you need another atom or another neutron to upgrade your thorium to uranium. But then you have this 0.35 extra. That. So you can generate a little bit more fuel than you consume all the time.
So instead of burning up an ever-dwindling supply of nuclear fuel, or even burning up as much fuel as it makes, the thorium fuel cycle lets us breed more nuclear fuel than it consumes. Once optimized, each reactor could generate enough fuel to start another every 10 to 20 years.
Possibly, but it's going to be as challenging of essentially a repurposing, reprocessing process as it is with uranium, which is why a lot of countries just simply don't do it. Which is kind of a shame, really. But if the economics aren't there, they're not there.
And those new reactors could do the same. That means doubling nuclear capacity every few decades without burning through the world's uranium reserves.
And if you're going to do that, you still wouldn't just use thorium, though. You're going to, at that point, economic forces are going to drive uranium, the cost of reprocessing or breeding uranium as well, in addition to thorium. But overall, I can see eventually both of these working together. And again, mixed oxide fuels can work as well.
If you want to have 10 or 20 or 100 times more energy on this planet, then we need what is called breeder reactors.
This is the thorium dream and Copenhagen Atomics' ultimate goal, to build a breeder reactor. But to encourage a fundamentally different reaction, they need a fundamentally different reactor, the Molten Salt Reactor, or MSR. This is where things get more interesting and safer. Molten salt reactors using thorium aren't just efficient, they're designed to avoid meltdowns altogether.
So, as are uranium reactors, every nuclear reactor is designed to avoid meltdowns altogether. Though, since we're talking about MSRs, it's already liquid, so you could argue you've already melted down, but in a designed and safe, controlled way. But that's because of the MSR design, not necessarily because of thorium. You could use uranium in an MSR design.
Unlike traditional reactors powered by solid fuel rods, MSRs are powered by uranium and thorium dissolved into molten salts.
Yeah, so you've already melted down. I know, but And here's the other thing. Meltdown is usually thrown around as the big boogeyman, scary nuclear accident thing, but you can have a meltdown in a nuclear reactor and everyone be fine. And I'm not talking about this reactor. I'm talking about a regular uranium solid fuel reactor, and that's why you have a reactor containment building. Like in 3 Mile Island, the amount of radiological release, and that's the key parameter of concern, by the way, in terms of how much you are dosing the public when operating your reactor, was basically insignificant, at least when you compare it to something like Chernobyl. Because Chernobyl, yes, it did melt down, but that wasn't the scary part. They blew up their reactor and had bits of core chunks everywhere and were releasing a whole bunch of fission products because they had no containment.
Because the fuel is liquid, waste products from nuclear fission can be extracted with the reactor still running. This continuous cleanup keeps the thorium to uranium reaction humming along by preserving neutrons for fuel production instead of letting them get soaked up by the waste.
So that's true. Also, safety is enhanced through this passive design, and it will breed, though you're still going to have to shut down the reactor to do maintenance on reactor components, not necessarily refueling. And also, the turbine building is going to have to require maintenance that the reactor is going to have to be offline for. So you're still going to have to shut down the thing, and outages are going to be potentially longer, just because you're dealing with molten salts.
Liquid fuel salt acts as a coolant too, circulating out and back into the reactor core to deliver heat for the power generation. In Copenhagen Atomics' layered onion core MSR, these hot salts are flanked by heavy water that slows down the neutrons so they can be better absorbed by thorium in the salt.
Yep.
And the outer layer of the onion will be a breeding blanket, where additional thorium salts will absorb neutrons produced by the chain reaction within the reactor core, breeding uranium-233.
It has layers like an onion. This is actually a pretty good explanation.
In the final design, this uranium will be transferred from the blanket to the molten salt fuel in the core.
When you have liquids, you can actually separate these things out. And it's a mix of chemistry and electrochemistry to do that, but it's a completely autonomous system that runs inside the reactor.
It is a lot more complicated, though, all those different intersecting loops. So if you have moving fluid, exotic moving fluids, so just considerably more maintenance needs to be done, and I could picture the outages being longer, though they would also happen less frequently, so it's going to be kind of a trade-off. And if you're using a modular design, you can just stagger the outages so that you're still producing power and you're just turning off a few reactors at a time rather than shutting down an entire facility. So that's cool.
While the reactor's operating.
Another massive advantage of MSRs is that unlike traditional water-cooled reactors that operate under high pressure to keep the water from boiling, molten salt reactors run at atmospheric pressure. That means no risk of high-pressure steam explosions and sudden loss of coolant or rapid overheating.
So you don't have the high pressure, that's true, but you do have high temperatures. And molten salts are quite corrosive at these high 700 Celsius plus temperatures. And they're quite chemically complex, especially when the fuel gets dissolved within the salt. They're hygroscopic, which means it reacts with water vapor and air. So the point is, it's still a high energy system, and there's just hazards associated with that energy. It's not under pressure, but the high energy used to create a nuclear power plant has got to go somewhere. And it's ultimately a trade-off. So you're trading pressure hazards for chemical hazards at this point. Not to mention, these are probably going to want to be located near molten salt plants, possibly at the same site. Just going to create a different, so the safety and operational challenges are just going to be different. It's going to be more about chemical reactions than meltdowns. After all, you're already melted.
A breach occurs. The molten salt simply cools and solidifies, trapping radioactive material and minimizing contamination. Many designs, like Copenhagen Atomics, even include frozen plugs at the bottom of the reactor vessel. If the system overheats, the plug melts, and the molten salt drains by gravity into a shielded dump tank, passively shutting down the reaction and preventing a meltdown.
And that's
I still can't handle with the preventing a meltdown. It's like, okay, lowering your risk of radiological release. I mean, your stuff is already molted. That's just funny.
Walk away safety, that means that if all the electricity is gone, if all the people run away, it's still safe. It's safe by itself because it has passive decay heat removal.
But while thorium reactors are walk-away safe, they're not exactly walk-up safe. A small amount of uranium-232 forms during the production of uranium-233 and gives off intense gamma rays powerful enough to pass through centimeters of lead.
And you're showing a picture of a weapon here? Okay.
That makes uranium-233, which could otherwise be an ideal bomb material, a logistical nightmare to steal or weaponize.
You see, and now we're getting back to part of the reason why thorium wasn't considered as much during the Cold War. And I'm just going to say this is double-edged, because, yeah, it's better against reprocessing, but it's producing nuclear waste here, high-level nuclear waste, uranium-232. It's kind of interesting logic here when you hear people talk about some of the advantages of thorium, because it's like, okay, it's less proliferation. Why? Because it produces more of this one type of waste. It produces less waste overall, but it produces some nasty gamma emitters. So it's kind of, so which is it? Well, thorium's going to produce less transuranic waste, but you're still going to have, and I'm talking by volume, but you're still going to have a lot of waste products. I mean, after all, you're dealing with fission. Uranium-233 has a roughly similar fission product spectrum as uranium-235. It's a little different. Here's the Dolly Parton curve, if you will, for uranium-233, 235, and plutonium-239. They're reasonably close. And of course, it's called Dolly Parton for highly scientific reasons. But some notable trade-offs. So uranium-235 is going to produce more cesium-137, which is worse. But uranium-233 is going to produce more strontium-90, which is worse. So kind of a wash.
However, it also means that Copenhagen Atomics will have to go to great lengths to keep that radiation contained.
Oh, yeah.
The plan is to avoid sending humans anywhere near the reactor containers. Each unit will be sealed in a steel box at about a half a meter or 20 inches thick that will weigh in at 1,000 tons.
Yeah, gammas can go through 8 inches of lead, so it's good that they're doing that.
Ship in 40-ton sections and be welded together on site. Copenhagen Atomics will house 25 reactors in a single building. Remotely operated cranes and forklifts will handle the heavy lifting, keeping the process as hands-off as possible in order to cut down radiation exposure and red tape all in one go. While gamma radiation makes thorium reactors...
Well, it's just making it more efficient. I mean, that's a good facility design. You're going to want to have backups like manual overrides, just like anything, just like you do for anything, but implementing more remote technology is always good.
It's trickier to handle. Nuclear waste from thorium reactors is actually much easier to manage. That's because fission products from traditional uranium...
I wouldn't know about much easier, but I'm okay saying easier.
235 reactors includes plutonium and other elements that stay dangerously radioactive for tens of thousands of years. The waste from uranium...
So, radioactive, as in it's going to be above background levels for tens of thousands of years, but we're talking, but very highly radioactive, more on the order of a few hundred. And thorium is better. It's more of on the order of 100. So definitely better, but we're not comparing hundreds of years versus tens of thousands of years. I don't like the term dangerously radioactive, but it will be well above background. But if you're putting the fuel in repositories or reprocessing or any other thing that you should be doing, then you should be good.
Uranium-233, bred from thorium, on the other hand, decays much faster. It's kind of like choosing paper or plastic at the checkout lane.
Yes, but the main hazards are the fission products. The uranium is going to last longer, but the radioactivity level is much less. That's one common misconception out there, that people assume the uranium is the bad stuff. It's the fission products. You can touch fresh, unused uranium fuel rods, albeit they're within their protective cladding, and you're not going to get much dose. Do not do that with spent fuel pool. Do not do that with spent fuel, however.
Because instead of needing to store spent uranium fuel underground for tens of thousands of years, or even 100,000 years, thorium reactors' waste can often be safely stored above ground for just a few hundred years.
And here's the thing, a lot of uranium waste is safely stored above ground in dry cask. Not sure why he's showing biohazards here. Dry cask storage does not include getting mixed with viruses. This is blatantly wrong.
And it gets even better. The bit of fissile material that's needed to start the thorium chain reaction can come from the waste of a traditional uranium reactor, allowing thorium systems to actually burn small amounts of legacy nuclear waste.
Also why they can be done together in mixed oxide arrangements.
Copenhagen Atomics plans to build this into their design, making their thorium reactor not just a fuel breeder, but a waste burner. So with all the advantages, how and when will Copenhagen Atomics commercialize the reactors? Well, thorium reactors demand much more than just new fuel. They also need pumps, pipes, and control systems that can survive a constant bath of corrosive salt as hot as lava.
Yes. And that's where you get into the whole designing for chemistry thing.
Not just the heat or corrosion, it's the neutron bombardment from the core that slowly wears down materials at an atomic level.
That's called neutron embrittlement. It is something that needs to be accounted for in designing both reactor vessels and reactor containment domes.
And because the core also blasts out intense gamma radiation, these systems can't be serviced once the reactor is up and running. They have to work flawlessly for years.
Which is why you need outages. So in order to manage this chemistry, it takes longer. So outages are just going to be longer, just in general.
Years, more like a sealed battery pack than a conventional machine. Here's how Copenhagen Atomics engineers are rising to the challenge. They've developed a molten salt pump that they say can run literally red hot, circulating a molten cocktail of fluoride, lithium, sodium, and potassium that's also known as FLiNac. I think that's how you say it, FLiNac. This salt mix exits the core at 700 degrees Celsius or 1300 degrees Fahrenheit and loops back in at around 600 degrees Celsius or 1100 degrees Fahrenheit. Now, to avoid the wear and tear that dooms traditional pumps, this pump levitates its rotating parts on magnetic bearings, keeping the system humming for years. In preparation for going nuclear, the company is running molten FLiNac through dedicated test loops to shake out the problems and fine-tune the performance of the pump, the sensors, heat exchangers, and even the custom steel alloy that's used inside the reactor. The steel can endure corrosive salts and neutron bombardment for at least 5 years, after which the reactor module is shut down and swapped out for a fresh one.
Okay, so here we're talking about lifespans of 5 years. All right, so we're just talking about plug-and-play reactors. There's no refueling for this particular design. There would be at some of the larger scale molten salt reactors, but here they're one and dones.
That's right, just 5 years. In traditional solid fuel reactors, corrosion and radiation mostly wear down the fuel rods and their cladding, which are components designed to be swapped out during routine refueling. But in molten salt reactors,
routine, we're talking 18 to 24 months.
The fuel is dissolved into the circulating salt, which flows through nearly every part of the system. That means the entire reactor module, core, pumps, and pipes takes the hit. So instead of just replacing fuel rods, you eventually have to replace the whole unit. Ironically, the fuel and water module
eventually, and but that doesn't happen very often. Some of those can even last upwards of 40 years, 60 years. Some of them can even have some modifications done to them. But yeah, you're going to need to replace a lot of stuff over that sort of lifespan. But having to produce something at scale that lasts that long also has its advantages as well. So I guess you can argue that's one disadvantage of modular technology in general, is that you're essentially wasting stuff, but versus having, pipes, vessels, components last for decades. But that I would put in it just kind of depends on what your power needs are, and as far as which option is superior for you. If you need lots of baseload energy that's not going away anytime soon, build a large-scale reactor. If you're into one that's in a less populated or less stable energy demand area and you just want to get some power out there but replace it, then yeah, modular design will do it.
Generator gets saved.
And then the fuel salt and the heavy water, that can be reused. So the fuel salt and the heavy water is just the same, being used over and over and over again. And that's also the expensive part.
It can be reused, but you're going to have some leakage eventually. So it's not like you're never going to have to replace it, necessitating the need for your chemical plants to make the salts.
Even with frequent reactor swaps, Copenhagen Atomics still sees a path to low-cost power. And Peterson is quick to note the upside.
But the great thing about that is that every 5 years you are able to upgrade your technology Whereas now with the classical nuclear reactors, they run for 50 or 60 years, and it's still the old technology from back in whenever they were built. But
now that's true. Retrofits do happen, and a lot of time they are going to happen during outages, but that is one component, is you are going to get chances to upgrade. But at the same time, 5-year planned obsolescence isn't necessarily something you see on for large scale energy production anyway.
In our case, we will keep on, even after 50 years, it's still 5-year-old technology. So that's sort of a plus in terms of keep on improving the efficiency of the system.
The company's next step is trucking a full-scale prototype reactor.
I'd say that's more mixed than plus. It depends on what your customers need.
Down to the Paul Scherrer Institute in Switzerland. That's the country's premier research campus for nuclear energy, with both a hot lab to handle radiation and an administration to handle the regulation. This public-private experiment will mark the first time a nuclear chain reaction kicks off inside of one of Copenhagen Atomics reactors, and the first time a thorium reactor is tested in Europe. The reactor will be powered by enriched uranium in the core and contain thorium in the surrounding breeding blanket. The test is slated for—
Yeah, you're going to need uranium to start the thing, or some really crazy neutron sources. Otherwise, you're just not making fission.
2026 and will run for up to 30 days at just 1% of the reactor's expected power output, but critically, enough to validate computer models. Over the following 4 years—
That's true. You can validate computer models at very low power, even less than 1%. That's one thing that's done after each refueling outage is the new core is tested. It's called low power physics testing, where the reactor engineers bring in a separate computer to do that in the control room.
Years in partnership with PSI, Peterson's team plans to begin transferring uranium-233 bred in the blanket into the core, an essential step towards a self-sustaining reactor that only needs refueling every 3 to 5 years. That's far less often than
3 to 5 years. I guess if you're operating in a staggered approach, but I figured it would have been a firm 5.
Traditional reactors, which are refueled every 1.5 to 2 years. The team will also optimize systems to clean fission products out of the fuel salt, with the reactor still running.
Note that he said traditional reactors, because again, this is kind of shifting to talking about one specific design here. You can design uranium breeder reactors to refuel every 5 years too. It's just different sort of mix and match constraints here. It's like, do you want it to be a breeder? Do you want it to use molten salts or water or gas or whatever as your coolant? And what do you want as your moderator? Do you want water? Do you want graphite? I mean, it can... I don't want you to walk away from this video thinking that this is the only way to do thorium, because it's not.
Keeping the nuclear chain reaction chugging along at a steady clip. For now, their biggest holdup isn't technology, it's regulation. They've got to scale a Matterhorn.
That's true for any new reactor design is regulation. So at least for their region, novel fuel form, using molten salt, as well as their coolants and moderators, novel reactor operation in general. They do have passive safety, but it hasn't really been gone through the extensive testing required. Yeah. No country currently licenses commercial thorium molten salt reactors. And again, I'm combining all of those into one, because that's what we have here in this particular design.
Enough paperwork before testing can begin in Switzerland. The PSI is on board, but there's no ski lift through the nuclear approval, and the pass isn't cheap.
I mean, one of the most expensive things are these licenses and approvals. I assume that once we have built more than 100 of these reactors, then the price of all this licensing and approval will also come down.
While Copenhagen Atomics gears up, China...
Part of it is there's a learning curve for the regulators themselves of how to regulate.
...appears to have crossed the starting line. In October 2024, a state-sponsored molten salt reactor ran at full power for 10 days with thorium and uranium in its fuel mix.
I would be sketchy looking at any of these things sent out from China. It operated at full power for 10 days, so it tripped. Yeah.
Bred protactinium-233, a clear sign that nuclear breeding was underway.
Okay, so precursor. Protactinium-233 is useless by itself for causing fission, but it is at least the intermediate step. Yeah. Operated at full power for 10 days with thorium fuel. I'm curious how much of that was just the uranium-235, and the fact that they're bringing up protactinium-233 but not uranium-233, that's a little sketch.
In April 2020,
sure, there's progress.
25, Chinese researchers announced they've topped their reactor up with fresh fuel without first shutting down, another early milestone on the road to continuous operation. But no one has claimed the prize just yet. Neither China nor Copenhagen Atomics have demonstrated a true breeder reactor that produces more fissile fuel than it consumes. Copenhagen Atomics believes...
Well, that's going to take a bit, even after operation, because breeding isn't like... In order to really make that definitively, at least when I think of making it definitively, what you need to do is make fissions with the fuel that has been bred. Not just, oh yeah, we have some stuff in our waste pile that could theoretically somehow possibly be used to make fuel at some point. It's like, all right, that's going to take some time.
Hitting that milestone, along with producing reactors at factory scale, could drive energy costs as low as $20 to $40 per megawatt hour. Just a quarter of today's average for nuclear energy.
And what's interesting is in some parts of the world, the cost is already lower than that, like in Texas sometimes a year.
To hit that price point, the company is reimagining not just the reactor, but the entire business model. It won't sell its reactors. Instead, it will build, site, operate, and eventually decommission each reactor itself, all without taxpayer funding, in exchange for taking the heat on nuclear installations.
So designer and an operator. That's two very different business models and skill sets. Yeah, that's I'm not saying it can't be done. I'm just saying that's a lot more steps that are integrated into one company than typically is.
Its clients will literally take the heat the reactors produce for use directly in industrial applications or for the conversion into electricity, but taking full responsibility.
Okay, so they're taking the heat portion, not the electricity. And that's also a different dividing part, because a lot of the owner-operators take it to electricity. So, yeah, different spots of drawing the line. That's actually fascinating. They're really focusing on what they're good at.
Everything from site evaluation to nuclear waste management, Copenhagen Atomics could make nuclear power viable even in countries that have never had nuclear power plants. Indonesia is one example, and that also happens to be the company's first customer. The plan is to use the energy from the thorium reactions to produce hydrogen and ammonia. Electrification isn't always the...
So if they're going to be the ones that do that, then let's say this takes off, then they're probably going to be the experts of managing regulatory environments, because it's different in every country. This company could develop itself into a law firm if it goes that way.
The answer. And nuclear reactors provide something solar and wind can't. Ultra-low emissions heat for everything from producing ammonia and smelting aluminum.
Not to mention base load, but yeah, heat.
To drying paper. And thanks to thorium, nuclear energy's ongoing headache of radioactive waste may soon go from a 100,000-year curse to a 300-year chore.
Both of those are high. Maybe in terms of what you're actually talking about, crazy, hazardous stuff, a 500-year thing that's going to require managed efforts to a 100-year thing that's going to require managed efforts.
Copenhagen Atomics expects to go commercial within a decade, with the biggest breakthrough, which is a self-sustaining breeding reactor fueled only by cheap and abundant thorium. That's a milestone with an uncertain timeline.
Yeah, because you're not necessarily using just cheap thorium. You're using all the components necessary to build anything is expensive. Making all of the molten salts is expensive. Or making the large pressure vessels if you're going to go the pressurized water reactor route. The fuel source is just one thing, and this is just one example of an application with that fuel source.
But it's also a technology our planet can't hardly wait for, because energy unlocks solutions and thorium might just give us the key.
It's not the only, it can work hand in hand. There's not just one solution. It will add diversity to the nuclear energy portfolio. And I'm excited for it. I do not see it replacing uranium. I mean, after all, the thorium isn't actually what you're fissioning.
But what do you think? Is it still worth the pursuit? And is this technology in the bag, or is it more of a roadmap than a reactor?
Well, let's see. The technology is going to involve learning curves with a thorium fuel cycle, learning curves with managing molten salt chemistry in the case of this type and any other design that involves that. Even online fuel reprocessing, as good of an idea as it is, it's still going to involve challenges and learning curves. After all, trying to do outages without it being an outage in a hot, high radiation environment is indeed a challenge. The U-232 contamination is a double-edged advantage, but it is still a radiation hazard, just like anything else. There's regulatory hurdles with operating new fuel, new reactor designs. It might actually be easier depending on what the regulatory environment is, in order to just do thorium fuel and keep a pressurized water reactor, do a mixed oxide fuel, do a uranium-based fuel as in a molten salt reactor. I mean, we're talking about the regulator, so not necessarily economics or science at this point. There's supply chain issues with building anything. There's draining and cool down issues with the vaunted passive safety systems. It's exciting to see, but I don't like claiming anything is the one solution that's going to help nuclear power or something. This one I feel was kind of a mixed bag. It had some great... This one was mixed. Had some good explanations, but also still a few misconceptions. Thanks so much for the recommendation, and thanks so much for watching. I'll see you next time.